Hi, we are going to discuss how to analyze the graph of first derivative. So we have this graph here that's given to us. It consists of a semicircle here centered at 2, -2 and two linear, two-line segments. Okay, so what we have here is, this is actually the graph of f prime. And we know that f of 4 is -5. So this is the information that's given to us. So the first question is, where is f increasing and why? So what we know from the first derivative test, a function is going to be increasing when its derivative is positive. So this is the graph of the derivative. Where is this positive? It's going to be positive from this point to that point. That is 7 to 12. Okay. So f of x is increasing on the interval from 7 to 12 because we want to explain that f prime of x is positive on that interval. Okay, that's as simple as that. Where does f of x have any relative extrema and why? So for relative extrema, our first derivative needs to have a critical point and have a sign change. So we are looking again, this is the graph of the derivative of the function. So we do have a 0 at 2, but at 2, even though the derivative is 0, the sign of the derivative does not change, it stays negative. We'll have a sign change at 7, where it changes from negative to positive, and we'll have a sign change at 12 where it changes from positive to negative. So we have 7. So at x equals 7, f of x has a relative minimum because f prime of x changes sign from what to what? From negative to positive. Okay, so right here the sign of the first derivative changes from negative to positive, and here it changes from positive to negative. So at x equals 12, f of x has a relative maximum. Why? Because f prime of x changes sign from positive to negative. Okay. Alright, we're going to go to our next question. I will have the graph available to us. So the next question here is, where is f concave up? So concavity deals with the second derivative test. That means we're going to need to think about f double prime. So what do we know about f double prime? F double prime is the first derivative to this graph. So the derivative to this graph will be the derivative of the derivative, which will be f double prime. So what do we know here? We know that the derivative to this graph, which will be f double prime, is going to be positive here and also will be positive here. Right? Positive here because the slope of the tangent line is positive, and also here. So that's from 0 to 2. So it's going to be concave up on the interval from 0 to 2, and also where else? On this interval here from 4 to 10, positive also, and 4 to 10, because how do we know that? We know that f double prime of x is positive on those intervals. Where does the f of x have points of inflection and why? Alright, so we need the sign change for the second derivative. our second derivative positive here. That's the first derivative to this graph. Positive here, negative here. At this point, we have a sign change for f double prime. We have a point of inflection. And also at this point, positive, negative. So 4 and 10. I'm sorry, 2 at 10. At x equals 2 and x equals 10 because f double prime of x changes sign at those points. Right? And we have a couple of problems here on the application of the second fundamental, well, one of those fundamental theorem of calculus, depending on your textbook. So what we have here is we want to find f of 12. So how do we find f of 12? Well, we know f of 4. Unfortunately, we have a graph of the derivative of the function, not the function itself. But we know that if we want to find this, then f of 12 can be evaluated as f of 4 plus the net change from 4 to 12, which will be expressed by the integral of the derivative. Right? So, how do we find this? We know f of 4. Why are we using 4? Because that's the one that's given to us. That's negative 5 plus. Now we have to use a little bit of geometry. So now we have to go from 4 to 12, right? 12 is right there. Right here. It's 12. So we're starting here. If you look at this triangle here is below the x-axis, and this triangle here is above the x-axis, but they have the same area, except one's positive, one's negative. Those two will cancel each other. So the only thing that's going to matter here is whatever's going to be extra here, because those two cancel each other. So the area of this triangle will be 2. So this integral here will be 2. And the answer is negative 3. Okay. Now we need to find f of 0. So since f of 4 is the only value that's given to us, we're going to have to use that. So to find f of 0, we're going to do f of 4 plus the integral from 4 to 0 of f prime of x dx. So this is the same setup that we used for the previous problem. Here's one dilemma. This integral, the limits are inverted, and this sometimes presents a challenge for some students. So let's do this. Let's change this to a minus integral from 0 to 4. So what we did is we flipped the limits to make it more how we prefer that, and then we have to negate the integral. So we're trying to find this integral here from 0 to 4. That integral here is going to be the area enclosed by this semicircle. So you would have to do the following. You would have to find the area of the rectangle minus the area of the semicircle. And since it's below the x-axis, it will be negative. So f of 4 is negative 5 minus, so the area of the rectangle here is going to be 8, 2 by 4. And then you subtract the area of half a circle with the radius 2. So it's going to be 1/2 times pi times radius squared. But let's remember that this was below the x-axis, so we have to negate that. And now we have a setup with that. If we complete that, we will be able to find the value. So what do we get? We have 5. Let's finish this first. Oh, I'm sorry, negative 5 minus. So what are we getting inside? There's going to be negative 8, right? And then there's going to be minus and minus plus, and this is going to give us 2 pi. So we distribute the negative. Now we have just some basic arithmetic. Plus 8 minus 2 pi, and the answer is going to be 3 minus 2 pi. And that's how it's done. Hope this helps.